Let's talk about the three conditions of stationarity. The first one being that the mean does not depend on time, that mu xt is equal to mu. Note that there's no t subscript there because it doesn't matter where we are in time. We're assuming the mean to be mu. Same idea for condition 2, except we're talking about the variance, that the variance does not depend on time, that sigma squared xt is equal to sigma squared. Notice no subscript of t because for across all time we're assuming that the variance is sigma squared. Note also that we're talking about the standard deviation as well because the square root of the variance is the standard deviation. So sigma xt equals sigma, doesn't depend on where we are in time. Notice also that we're talking about that the variance and thus the standard deviation are also finite. That will become very important when we talk about non-stationary time series, but that is an added condition of stationarity. So finally, we want to talk about covariant stationarity in that gamma xt1 and xt2 depends only on t2 minus t1, how far apart we are in time, not where we are in time. So where we are in time might be early in the series, middle in the series, later in the series. We would assume that the covariance is the same no matter where we are in the series, be it early, late, or somewhere in between. So that's going to become more clear when we talk about these examples that are coming up. So let's go ahead and get started in these examples. Great. So here is the first example. We've got time. We'll call that 1, 2, 3, 4, 5, 6, 7, 8. Let's just do 8, 7, 6, 5, 4, 3, 2, 1. That is time. And we'll have xt. So say we've got 4 realizations here. So I'm going to use my pink marker again, but let's say that we've got one that kind of does like this. Another one, just a convenient toy example. Let's say we look at, let's look at another realization. It just kind of wanders around about the same. And we look at another realization. It has a different starting point, but it just kind of wanders around about the same behavior. It kind of just looks like the ocean here, right? It could look just like this. Again, just a toy example, but let's see kind of what we mean. This is only a sample of 4 realizations from a process that we're trying to estimate the parameters of. But looking at x1, we're going to put a pink dot. Again, pink doesn't have any meaning here. Just the dot, I'm going to say, represents x bar t for where that could be x1, x2, x3. So for x1, it looks like the sample mean of those 4 time points would be right about there. For x2, it looks like it would be pretty close to that. And for x3, right? That one's a little lower, that one's a little higher, a little lower. Maybe it'll be a little bit lower. I'm just looking at those. This one might be a little bit higher. But looking at those 4, here, these 6, right about there. 7, too high, too low. It's going to bounce around a little bit. But my point here is that these would be really consistent. If we could get an infinite number of realizations, we would be assuming that the mu1 and mu2, that the mean of all of these realizations would be the same as the mean of all these realizations across all 8 time units there. And if that were true, I'd expect the sample means to be about the same, and that's what I see here. That this sample of 4 realizations have sample means that are very consistent with the concept that mu xt would have the same mean. And we'll see, that'll kind of take shape a little bit better when we see an example where that's not the case. But right here, clearly all of 8 of those x bars are pretty close to one another, which would be really consistent with them all having the same mu. That mu1 equals mu2 equals mu3 all the way to mu8. So we don't need a t subscript, we'll just call that mu. So now let's look at the variance. On average, how far apart are these 4 points away from the mean? And is that consistent with the entire population having the same variance from 1, 2, 3, 4, 5, 6, 7, and 8? So looking at these here, just kind of the range looks pretty consistent across 1, 2, 3, 4, 5, 6, 7, 8. And thus the average distance each of these points is away from the green dot. That average distance looks to be about the same no matter where I am in time. And that would be consistent with the idea that sigma squared xt equals sigma squared. Awesome. So let's talk about condition 3. And in condition 3, we're talking about the covariance. So we have to define for each t2 minus t1. So let's just, as an example, talk about if t2 minus t1 was 1. So if that was the case, we would have, like, these 2 are 1 unit in time, so that's 1, 2, 3, 4, 5, 6, 7. We have 8 observations, so at lag 1, where I'm talking about one time unit apart, I can look at that. That happens 7 times. So, so looking at these pairs here, I'd say, well, at lag 1, it looks like the pink from 1 to 2, they went from 1 above the mean to 2 above the mean. What about the green one? Above the mean, above the mean. What about the yellow one? Below the mean, and then in 2 it was below the mean. And what about the blue one? So below the mean, below the mean. It has the same behavior. All four of those all 4 realizations have the same behavior at lag 1. If one's below the mean at time unit 1, at time unit 2, it tends to be below the mean. Whatever side of the mean it tends to stay on that side of the mean from first observation to the second observation. Is that true in the middle of the series? Well, let's look at 4 and 5. Yep, above, 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 below, 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 below. Those are behaving the same in the beginning of the series as they are in the middle of the series, and the same as in the top of the series. Clearly, from 7 to 8, that's above, above. That'd be above, above, below, 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 below. So as far as covariance is concerned, those would all, no matter where I am in time, it would be indicative of a positive covariance. Okay, so I'll say here that is only at t2 minus t1 equals 1. That would have to be true no matter how far apart we are in time, that autocovariance would be the same no matter where I am in time. So I'm just going to write for that here gamma xt1 xt2, and we'll just say check. Right? That's not a proof, but that data there is consistent with if that were true. So this should shed some light on exactly what we're talking about as far as meaning is 1, 2, 3, 4, 5, 6, 7, 8. Let's say this time we had a series that maybe started down here and then wandered up here. And then another one that maybe started down here and then wandered up here. And then another one that started down here and then wandered up there. And then a final one that started down here and then wandered up here somewhere. Okay, so doing the same idea here, letting the dot be the xt, I look at time 1 here, I see, okay, the mean is right about there. If I really look closely, the mean of those 4 observations at time 1 is pretty low there. And up here, that would be high, high, low, low. Okay, I'm going to say that is right about there. Right? Doesn't matter that it's pink, remember, just remember it matters that it's a dot. And so that would represent the sample mean at time 1, and that's the sample mean at time 8. And if that were the case, that might be some evidence that mu1 is different than mu8 because those are much farther apart than they were up here. Right? And right now that's subjective. We could run a hypothesis test on or whatnot, but this would be consistent with if mu1 was small and mu8 was big, we would expect to see something like this. So that data would be consistent with, get rid of that, consistent with mu1 being less than mu8. Okay, let's move on to condition 2. In condition 2, I see that these are in a really compact space, that the average distance that each of those observations at t equals 1 is very small, that each of those distances from their respective mean on the dot is relatively small compared to what they are at 8. Those are relative to this, the average distance is much farther per observation away from the mean. And that would be, again, not a proof, but that would be data that are consistent with sigma squared 1, the variance down here, being less than sigma squared 8, the variance up here. So that would be a violation so far of condition 1, and condition 2 would look something like that, or that would be evidence in that direction. But what about the covariance? Right? What about the covariance? So let's again talk about at lag 1. So 1, 2, 3, 4, 5, 6, 7, 8. And let's check it out. So we'll have to put the means in here. So because covariance is with respect to the mean. And those look like they might be climbing. This is kind of more evidence of increasing mean over time. So when I look at that, Again, pink doesn't mean anything. It's just that it's a dot that represents the X bar at that particular time point. So again, that's more evidence that over time the mu's are increasing from 1 to as we go from mu1 to mu8. But let's check out the with respect to the mean how it's working at 1 unit in time difference. Early on in the series, let's see here, the pink goes from 1 to 2, it's above. Okay, and the green as we go from 1 to 2 is above and above. And the yellow to me here looks like below. And as I let the blue go from 1 to 2, it's below. So if it starts below the mean, it tends to end below the mean from 1 to 2. And if it starts above the mean, it tends to end above the mean from 1 to 2. So that would be consistent with positive autocorrelation at lag 1, from T2 minus T1 equaling 1. But that's just early in the series. Maybe it changes later on. So checking out, let's just look from 4 to 5. So from 4 to 5, let's go to the pink. The pink is above its pink dot. It's above its corresponding mean, sample mean. So from 1 is above. And the green is above. And the yellow is clearly below. And the blue is below. Again, very consistent with positive autocorrelation. So let's look on later in the series. Maybe let's just go all the way in here. 7 to 8. Above. The yellow now has gone above the mean, but it starts above and is above at lag 1. And at this point, right, by this point, it has gone below the mean, but I'm just looking at lag 1 unit in time. And in 1 unit in time, it started below and ended below for the green, and started below and ended below for the blue. Again, middle, or early, middle, and late, very consistent evidence of positive autocovariance there. So I would say this one is consistent with the autocovariance depending on how far apart I am in time, but not where I am in time. Great, and then we just looked at lag 1. Later on in the book, we'll look at lag 2, 3, 4, right? You're just looking at 2 units in time for lag 2, and you can only look at 6 of those pairs. Good kind of thought experiment. But let's look at one more that will really kind of maybe shed some light on this autocovariance idea, because so far we've kind of checked them off here. Let's say I've got 1, 2, 3, 4, 5, 6, 7, 8. 7, 6, 5, 4, 3, 2, 1. Again, that's time. We won't label that. Excuse me. And we're ready to go. Okay, so say we've got some more realizations here. And let's say that this one starts up here and then goes down here and then comes back up here and then goes down there. And then just kind of wanders around a little bit. You kind of already see that it's behaving differently here than it is here, but let's make that match kind of our definitions here. So let's have another one. Let's say another one goes from here. Let's say it goes down to there and then comes back up to here and then goes down to there, and then it just kind of wanders around a little bit. Just kind of wanders. Kind of feel like Bob Ross. You remember the old painter. So if we go here, we go from here, and let's say this one goes up first, and then down, and then up, and then from there it just kind of wanders around. Maybe it goes up again, maybe it ends back going back down. Beautiful. And then finally, let's just for example's sake say blue starts here, and it goes up, and then it comes down, and then it goes back up, and then once again it just kind of wanders around that way. Okay, so let's check that out. Again, we only have 4 realizations, but let's look and see what they're consistent with. Again, let's start with the mean. Well, the mean, if we put our little pink dot in there, those two look right about there. It's going to be really confusing because I put dots in there, but that's a dot. There's 1, 2, 3, 4. That dot looks like it goes right about there. 1, 2, 3, 4. That dot. Look at these. These sample means look pretty consistently in the middle. Right? That one looks to be right about there. This one, maybe that one's pulled up a little bit, but then it kind of settles back down, and this one's about there. So that sample mean, I'll just kind of follow it, connect the dots on the sample mean. Oh, that's going to be really confusing. X bar. So that's the sample mean. Maybe there is some evidence that it's increasing over time, but it's not going up very much. And maybe that's really consistent with the same mean. Maybe we'd put a question mark by this one, right? And say, well, there is some evidence that it's increasing over time, but it's not increasing very much. Maybe that could happen by chance if mu xt, if mu xt was equal to mu. But maybe we just put a question mark there because it does look like there's some evidence of it going up and down, but that's probably pretty consistent with the means being the same. What about the variance? So the average distance those dots are away from the mean there, okay? So we'll take that. That looks pretty consistent with that one. The average distance those 4 are away from its mean. Pretty good, pretty good. Those are pretty small, but every once in a while you're going to get a small sample variance, even if the population variance is the same. Back to normal. That's a little bit bigger, right? That's the one's a little smaller, that one's a little bit bigger, but they're not grossly big or small. I think those are all very consistent with the concept that sigma squared xt would equal a consistent sigma squared. Okay, certainly, again, not a proof, but that data looks pretty consistent to me. If you wanted to put a question mark by it, you could, but both of those are pretty close to what, if you had constant mean and constant standard deviation, what it would look like. Certainly not as egregious as from here to there, or from that little mean to that little mean. But now let's talk about the covariance. So the covariance here, if we look at that line that's representing the mean, the pink one goes above, and by the time it gets to 2, it's all the way down below, right? That's x1 for the first realization. That's x1 to x2. And then from, so let's just look at that. So then the green one, x1 above the mean, x2 below the mean. Oh, okay. How about the yellow one? The green one, x2 above, x1 above, x2 below. The yellow one, x1 below, x2 above. Okay? And then what about the blue one? x1 below, x2 above. So in each case at lag 1, wherever it started, if it was above the mean, it ended up below the mean. And if it was below the mean, it ended up on the other side above the mean. So whichever side it was on at x1, it was on the other side of the mean at x2. That's consistent with negative autocorrelation. And thus negative autocovariance. So great. So that's from 1 to 2. Notice from 2 to 3, it's the same thing, right? If pink was below, then it was above. This one was above, then it was below. This one was below, then it was above, and the blue was above, and then it was below. All 4 indicative of negative autocovariance at lag 1. Now let's move on into the series. And moving on, let's look from 6 to 7. Well, from 6 to 7, this one was above, above. The blue above, above. The pink above, below, but very small, right? They're very close to the mean, and then below, below. Let's look at another one from 7 to 8. So from 7 to 8, above, above. Blue is above and very close. This one's above, above. And then this one, or sorry, below, above. And then this one's very much below, below. So where it's not perfect on there, right? The ones that don't match below, below, and above, above are very close to the mean. Those would be very small values. Whereas certainly it looks, they're not as consistent down here, and it looks different. These look like they're wandering, whereas these look like they're what we'll call oscillating. Those look like they're oscillating from at lag 1, from one time point to the very next time point. Looks like it's more probable they'll be on the other side of the mean from where they were at the time before to the time after, whereas later on in the series, it's more likely that they stay on the same side of the mean when they move from one time point to the very next time point. So that would be indicative of, we could say early in the series, gamma x1, x2, or xt1, xt2 would be negative autocorrelation at t2 minus t1 equals 1. Right? We've got a lot of qualifiers here that the autocovariance at xt1, xt2 when t2 minus t1 is 1 would be negative. Every time early on in the series, when we move from one point to the very next time point, it's very probable that realization has gone from one side of the mean to the next. Whereas late in the series, Whereas late in the series, we say that is consistent with xt1 and gamma xt1, xt2. The autocovariance of xt1 and xt2 is greater than 0, right? That's a little more consistent with wandering behavior where wherever side of the mean you're on is, you stay on that side of the mean from one time point to the next. And these were switched, but they were very close to each other. That was very close to the mean, that was very close to the mean. Could have very easily shifted a little bit to have them on the same side. So that's more consistent with this being positive autocorrelation. When, instead of at, we can say when T2 minus T1 equals 1. So for the same T2 minus T1, it looks like it varies from early to late. From early to late, that's where, so that would be a violation of condition 3. So we'd say, nope, doesn't look like it's good for condition 3. So awesome. That is a look at the 3 conditions of stationarity. Keep up the good work.